All right, we've been talking about oxidation and reduction. I just introduced a new reagent that will make an epoxide in a single step. Our previous method for making an epoxide, one that's not that old, was to do halohydrin formation that puts an OH and a Br on adjacent carbons. And then if you use a base like sodium hydride, you can deprotonate the OH group, turn it into a good nucleophile, and then you're poised for an intramolecular SN2 reaction where you get backside attack of the oxygen on the sigma star and you close up the epoxide. Now, we can do this with a new reagent that I just introduced last time called metachloroperoxybenzoic acid. This is what the reagent looks like. You'll learn in 352, maybe you already know what this meta means. It refers to two things on a benzene ring that are separated by one carbon. Here's the chloro, here's the peroxy acid, and then the benzoic tells you that it's on a benzene ring. The key part of this molecule is this weak oxygen-oxygen bond. Often, oxidation reagents have weak heteroatom bonds, like oxygen-oxygen. And so I'll show you this mechanism. It's worth knowing, and it will help you remember what happens, though you may also just want to memorize this reagent. So I'll show for you what happens here, and it'll be best if we do this with a reaction where there's some stereochemical issues. So I'm going to show you a cis alkene, and we'll draw it as though it's on its side with these R groups sort of pointing towards us, and then the hydrogens pointing back into the page, and then this is sort of the plane that all of the carbons of the double bond are in, and then all of the atoms that are listed here are all in this plane. The reagent reacts with either the top face or the bottom face of the alkene with equal efficiency. I'm going to draw this reagent in a slightly different way. You'll see it's the same thing as I've drawn above. I'm going to use an R group for the benzene ring, the metachlorobenzene ring. And this is the oxygen that's going to get attached to both carbons of the alkene. We'll call these A and B. Everything else you can think of as a leaving group. Now that's weird because two parts of the leaving group are not really even attached to each other, which tells you that we've got some work to do with arrows. But basically, the leaving group is going to be a carboxylic acid. It's going to leave as the following neutral group. You've seen neutral leaving groups before. Water was a good neutral leaving group. We're going to do the same thing here with this carboxylic acid. What ends up happening is the pi electrons from the alkene attack the sigma star of that weak oxygen-oxygen bond. At the same time, lone pair electrons on that oxygen attack the other carbon. So far, this is pretty analogous to what we saw when we did the alkene halogenation reaction. We saw pi electrons attack the weak bromine-bromine bond, dumping electron density into the sigma star, breaking the bond, and then we saw lone pair electrons from the bromine attack the other carbon to create a three-membered ring. So that's exactly what's going on here. The only other arrow we had for bromination is we needed to break the bromine-bromine bond, so electrons from that bromine-bromine bond went on to the bromine leaving group. Now here I've told you that the leaving group is going to be this carboxylic acid, so this one arrow from the bromine reaction is going to be many arrows over here. So we'll take the electrons from the oxygen-oxygen bond, and they'll form a new pi bond between this oxygen and the carbon. At the same time, we'll break the oxygen-carbon pi bond over here with electrons going out onto the oxygen. And then finally, we'll take lone pair electrons on the oxygen, and they will pull the proton off that orange oxygen, and then those electrons will go there. Sort of a lot going on at once. That's okay. That's you can do intramolecular reactions like this when you have 1, 2, 3, 4, 5 atoms in a ring, or 6 atoms in sort of a row. The angles work out pretty well for this oxygen on this end to interact with that hydrogen. Some people have called this a butterfly mechanism because if you turn it around and sort of twist it to the left, that's one wing of the butterfly, that's the other wing. I don't really see it either. So, okay. Questions about that? No? Okay. Fine. That's worth practicing a little bit. It's interesting that a reagent like this can transfer a single atom to an alkene. The product of this reaction is an epoxide. Because the oxygen is delivered simultaneously to carbons A and B, there is no time for rotation around bonds, so that groups that are cis to each other in the alkene must necessarily remain cis to each other in the epoxide product. So this is a reaction where stereochemistry has consequences, and therefore it's a fun one to sort of ask questions about. If we had started with the trans epoxide, the trans alkene, and used this same reagent, MCPBA, the epoxide product that we get from this reaction would have to be the one where the R groups are trans to each other. And you can see already that this kind of thing has stereochemical consequences. The epoxide we got from the cis alkene is not chiral. It's actually a meso compound. Whereas the epoxide on the right is chiral. And if we get one enantiomer, we have to make the other. These enantiomers would come from addition of the oxygen to the alkene from above versus below, and that's how you get both enantiomers. All right. So that's one method for opening up an epoxide. Sorry, that's one method for making epoxides. And we can now, your text now introduces or reviews something that you've done before, which is opening up an epoxide with a nucleophile in a reaction that your text calls anti-dihydroxylation. So to understand this, it doesn't make any sense except with reference to the original alkene that you used to make the epoxide. So this is going to be a 2-reaction series. You're going to make the epoxide, and then you're going to open the epoxide with OH minus. And actually, you could also do this with water under acidic conditions. It turns out not to matter. But let me show you what we're talking about. If we start with that cis alkene and we use MCPBA as our making the epoxide, our first product is this meso epoxide. Then let's say we open it up with sodium hydroxide under aqueous conditions. What's the product there? Remember, in this mesoepoxide, carbons A and B are identical, so it doesn't matter which one we attack. I'm just going to show the product that would occur from attack of carbon A. So OH comes in and attacks carbon A. You get inversion of configuration at carbon A. Oops. That looks like this. And then I could just draw that as the product, though it may be helpful to try to redraw this in a way that helps us see the stereochemistry a little bit better. Let's see. I'm going to redraw the molecule such that the R groups and carbons A and B are all in the same plane. One of the OH groups would be a wedge, the other would be a dash. Of course, if I had chosen to attack carbon B instead of carbon A, I would get the other enantiomer as my product. You should be able to see that both of those products are chiral. The carbons A and B are stereocenters. And the way I've chosen to draw them here indicates that this is an anti-product in the sense that with respect to the original alkene, the OH groups are on opposite sides of that original alkene. So that's why we call that series of reactions anti-dihydroxylation. It's a two-step reaction, but it's almost as though the net effect of that two-step reaction is to put one OH group on one face of the original alkene and the other OH group on the other face of the original alkene. Okay, does that make sense? I mean, I know it makes sense when I'm saying it. The question is it going to make sense when you're in the testing center dealing with it? Because most likely, you're likely to encounter this situation where I show you this product and I ask you, how did you get that? What were the reaction conditions? And you're going to have to figure out what the stereochemistry of the alkene was that led to that product. So that's worth some thought and some practice. Questions so far? Yeah? Any of these reagents that work on double bonds, would they work on triple bonds too? So all of the reactions we talked about in chapter 10, you may not have noticed, but there was a little section at the end of chapter 10 that we skipped over about reactions with alkynes. Most of those reactions, halogenation, hydrohalogenation, hydration, you can do those on alkynes too. The only difference between an alkyne and an alkene is the alkyne has two pi bonds that can react. We skipped over that mostly because I felt the juice wasn't worth the squeeze. But yes, I don't know actually about MCPBA and alkynes. My guess is that if you did this with an alkyne, the intermediate would look like that. That's probably pretty highly strained and not particularly stable. I haven't seen any reactions of alkynes with MCPBA, but that doesn't mean they don't happen. It just means I don't know about them. All right, what else? Yes? These two products are enantiomers. So where did this come from? The three lines just represent these two are the same thing. You get this one from opening of the epoxide with OH minus on carbon A. I have simply redrawn it in a way that shows you that this is the anti-dihydroxylation product. That's just rotation around a carbon-carbon bond. Whoa, I didn't mean to do that. There we go. Just for maybe completeness, I'll show you the product you would get if the OH attacked a carbon B. And then that, through rotation around the bond between A and B, is equal to this. And so, yeah, we would call this the anti-dihydroxylation product. We added 2 hydroxy groups to adjacent carbons, and they are on opposite sides of the original alkene. Good. Others? Okay, so you should be able to work out then with this if instead we had started with the trans alkene. We use MCPBA, we get the trans epoxide. I'm going to use a plus and minus in parentheses here to indicate that we get both enantiomers. I'm only going to draw one. But then, if I use, again, sodium hydroxide under aqueous conditions, I'm going to draw the product that you would get if we attacked carbon, opened up the epoxide at carbon A. You will see pretty quickly that it doesn't matter which carbon I attack. If I rotate around this carbon-carbon bond, you can see that the OH groups are on opposite sides of the original alkene. When my R groups for my original alkene are in the same orientation that they were to begin with, you can see that the OH groups have been added to opposite sides of that alkene. But it's interesting to note that what I've drawn for you here is actually a meso compound. If I were to continue to rotate around carbon-carbon bonds, you should be able to convince yourself that this is the molecule, which is actually a meso epoxide. And so here's something that people in a hurry, a mistake people in a hurry always make. I might be inclined to draw this product, the meso 1,2-diol, with the OH groups on adjacent carbons, and say which alkene led to that product. And some of you are going to fixate on the fact that it looks like these R groups are sort of cis to each other, so you're going to choose the cis alkene. That's exactly the wrong answer if you're using MCPBA and hydroxide to make this happen. Okay, so watch out for that, because that'll happen. All right, other questions? So that's yes, go ahead.
If you attack the other enantiomer, will you get the same meso product?
Yes, if you attack, you'll get this same meso product if you attack carbon B. And then if you draw the other enantiomer and have attack carbons A and B, you'll still get that same meso product. Okay. It's kind of cool how that works out. Yeah?
Is it beneficial to look at stereochemistry in terms of the OHs in this case?
Is it beneficial to look at stereochemistry in terms of the OHs? What do you mean by that?
Just like looking at the OHs instead of the R groups, because you can do the exact same with R and C stereochemistry.
Sure, you could, instead of placing the R groups all in the plane of the page and having the OHs be dashes / wedges, you could, that doesn't change, yeah, you could leave the OHs in the plane of the page and have the R groups be dashes or wedges, that's fine too. I only show it this way because when you draw the R groups in the same orientation as they were in the original alkene, then it becomes obvious whether the two groups are anti to each other or not. Okay. We're going to muddy the water a little bit here because we're now going to learn to do something called syn dihydroxylation, which instead of anti, syn is going to deliver the OHs to the same side of the original alkene. Now we're going to have choices, but that's going to lead to an opportunity to get mixed up with stereochemistry. So there's going to be some things you got to do to keep the reagents straight in your mind and what they do. All right, anti-dihydroxylation is a two-step reaction. You need MCPBA, and then you open up the epoxide. What we're going to talk about now is syn dihydroxylation, which does exactly what it says. It's going to add two OH groups to carbons A and B of the alkene, and the OH groups are going to be added both to the same face of the original alkene to give you the desired product. So you're going to see this is complementary to what we did before with MCPBA, but the stereochemical relationships are going to be exactly backwards. So follow this through. Here is a cis alkene. I'm going to draw this in the same way as I drew the cis alkene for epoxide formation. We're looking at the plane of those trigonal planar carbons from the side like this. There are a few reagents that do this. I'm going to only hold you responsible for one. This is osmium tetroxide. Osmium is a transition metal. There are 4 oxygens. This is a really high oxidation state. That's a plus 8 oxidation state for the osmium metal. And I'm only going to show you this portion of the mechanism. Knowing this portion of the mechanism that I'm about to draw will help you remember that the process is syn rather than anti, but we won't do the second part of the mechanism. Pi electrons attack one of these oxygens. One of the electrons from the osmium oxygen pi bond, 2 of the electrons from the osmium oxygen pi bond go on to osmium. That's a reduction of osmium. Now afterwards it'll be in the +6 oxidation state instead of the +4 or the +8. I don't know. Sorry, making mistakes. And then we'll break the osmium oxygen pi bond here, and those electrons will go to form a new oxygen carbon bond with carbon A. So that reaction happens all at the same time in a concerted step. So I'm going to draw the intermediate that forms. It's a weird intermediate that you won't have seen before, or perhaps again ever. This is called an osmolate ester. And the only thing you need to know about this is that notice that the R groups that were on the same side of the original alkene are still on the same side of that 5-membered ring intermediate that we made. So in some ways, this should resemble a little bit what we did above with making an epoxide. Do you remember how the R groups here were cis to each other, and then in the epoxide they are cis to each other? In the same way, with syn dihydroxylation, the R groups that are cis to each other in the alkene remain cis to each other in this cyclic osmolate ester. That's concerted. It happens all in the same step. There's a second step to this reaction. In the first step, you just use osmium tetroxide. In the second step, you're going to use a reagent that's just not explained in your text. This is sodium bisulfite, and its purpose is simply to hydrolyze the osmolate ester. How do we even spell that? So all this reagent's going to do is it's going to add, and this is a reagent that comes with, it's aqueous, so comes with water. We're going to break the bonds between osmium and oxygen. We'll put new OH groups on the osmium, and then with these oxygens on the osmium will be liberated and end up protonated. You don't need to worry about really how that happens. All you need to know is that we release the oxygens from the osmium and we end up with this product. I'm going to redraw that product for you with the R groups in the plane of the page so that you can see that the two OH groups got added to the same side of the original alkene. Okay? So that's a syn dihydroxylation reaction. I do want you to know these arrows. You don't need to know how this second step of the reaction works. Yes?
So how do we tell the products of this reaction versus the other one you just showed us from that?
So how do we tell the products of this reaction from the other one? Well, take a look. The product here is a meso 1,2-diol. It is not chiral. If we use the syn dihydroxylation series, this 1,2 punch of osmium and then sodium bisulfite, the starting material for this syn dihydroxylation reaction must have been the cis alkene. Okay? But as you pointed out, if we scroll upward, here I have the same meso 1,2-diol that is not chiral. If you do not believe that it's the same thing, pancake flip it, and it totally is. But notice that if we're using anti-dihydroxylation as a strategy, the starting material was the transalkene. So the answer is you can use both methods to get the same product, but you got to start with the right thing. If you want to use anti-dihydroxylation to get the meso 1,2-diol, you need to start with the transalkene. Yeah.
Just follow up then. If this was on the test, if you were looking for like a specific starting material, would you say using anti-dihydroxylation or using syn dihydroxylation?
Uh-huh.
Or would you just be like, here's the product, good luck?
Right. So how could this work? Well, I mean, there's a couple of different ways that I could envision framing the question, but if this was the starting material and this was the product, then the answer's clear. There's only one answer, right? You have to use anti-dihydroxylation. If in contrast, this is the product and the cis alkene is the starting material, then you have to use syn dihydroxylation. I mean, I can also envision a question where I say, which of the following reactions work to give the final product? And you got to identify the two that work versus those that don't, or maybe, anyway. So yes, there's different ways you can format questions on this subject, but you see the complexity, because if you get mixed up on stereochemistry, this is a problem, because you have two different ways to get the same product, but those two ways start with different starting materials. Yeah. Okay? Yes?
In the MCPBA reaction, the nucleophile will attack the least substituted carbon.
Right, so the question is, when you open an epoxide, if you use a strong nucleophile, will it attack the least substituted carbon? Yes, but carbons A and B are identical here in this example, so that's why it doesn't matter here. Second, because your nucleophile is OH minus, look at your product, both carbons A and B of your epoxide have the same thing on it. You can't actually tell without some additional work which of these two oxygens was from the epoxide and which was from the hydroxide. experimentally, you could do some things to try to establish that, but for this particular question, you can't tell. You're right, though. The same issues with epoxide opening still apply. If carbons A and B are not equal, then the nucleophile that opens the epoxide will attack the least substituted carbon under negative charge conditions, the more substituted carbon under positive charge conditions. Yeah. Okay. Good. Just for completeness then, let's show you the trans alkene, and then I will draw for you the product that comes after opening after syn dihydroxylation. One way you could draw that product would be like this. The 1,2-diol that you make here is chiral, so we make both enantiomers. It might be useful to try to redraw this molecule in the same orientation as the R groups were to begin with. Doing so should help you see that the OHs get added to the same original face of the alkene. Okay, so this is a chiral 1,2-diol. You get both enantiomers. And again, notice that this is opposite the result of the anti-dihydroxylation. For the anti-dihydroxylation, if we wanted the chiral 1,2-diol, both enantiomers, we had to start with the cis product. But for syn dihydroxylation, if we want the chiral 1,2-diol, we have to start with the trans product. Okay, I'm telling you, that's going to be worth some practice, because that's a beautiful, complicated illustration of stereochemical consequences of reactions. All right. Other questions there? So we got a couple more reactions to do in this chapter. These are going to involve oxidation of alcohols to carbonyl compounds. So we'll call this reaction oxidation of alcohols to either ketones or aldehydes. And whether it's a ketone or an aldehyde is going to depend on what the starting material is. If the starting material is a primary alcohol, we can oxidize to an aldehyde. The reagent that we're going to introduce that does this is called pyridinium chlorochromate, or PCC for short. Pyridinium is a counterion. It's organic soluble, and so it helps the chromium part of this reagent be soluble in organic solvent. Chromium is here. There are, let's see, I forget. Nope. So this is the pyridinium portion, and this is the chlorochromate portion. As I said, the pyridinium is there for solubility, but you can think of it as just as a spectator counterion. The chromium and the chlorine are the key portions of this reagent. And chloro is a leaving group. So this mechanism, well, I'll show you the product of the reaction. The product of the reaction is an aldehyde. You can tell that this has been oxidized because we've lost a carbon-hydrogen bond and we've gained a carbon-oxygen bond. So that molecule has been oxidized. We've gone up one step in oxidation from the alcohol to the aldehyde. I haven't shown what gets reduced here. The chromium agent gets reduced, and you'll see that in a little bit. So let me show you the mechanism. Oxygen is the nucleophile. Chromium is the electrophile. We haven't learned a lot about metals in this class, and we really won't. But I will point out that this is a chromium 6 reagent. It's chromium in the +6 oxidation state. So that's 6 electrons lost relative to chromium metal. So this is an electron poor version of chromium. It's electrophilic. And so it makes sense that the oxygen could attack the chromium and the chlorine leaves as a leaving group. So we make a new oxygen chromium bond. Oops. So let's draw what that product looks like. Man, my penmanship is really small in these notes, and I'm getting kind of old. When you have to bring reading glasses to class in order to see your notes, that's kind of not great. Well, all right. So you have this weird intermediate that has a negative charge on the a negative charge on the chromium oxygen, and then a positive charge on this adjacent oxygen. What happens next is a series of proton transfers. Some of you are thinking, why doesn't the negative charge on this oxygen just pull the proton off of that one? And I don't like that for reasons I can't quite articulate. But it's the easiest thing to do. So I think maybe we'll just go with it. Anyway, anytime you propose a reaction that's intramolecular like this, you always have to worry, can the electrons on the thing that's doing the attacking reach the empty orbital that it's attacking? Think about this oxygen hydrogen sigma star. It's pointing off in this direction. Can that oxygen, which is sort of 90 degrees away from where it needs to be, actually reach around and get there? And the answer is maybe. Your text actually doesn't even bother showing arrows. I think in the mechanism shown in your text, it sort of glibly notes proton transfer, and then sort of expects you to come up with what happens. Oops. So I'll show you what the product of this proton transfer is. You can see that the proton, which used to be on the oxygen from our original alcohol, ends up on the oxygen from the chromium. If you want to imagine that it happens like this, that's fine. It may also be stepwise. Another molecule may remove this proton from this oxygen, and then in a second step, it may add the proton to the chromium oxygen. I'm basically going to be okay with either way. Okay, so this intermediate is called a chromate ester. And what you need to know about it is that all of this, including the electrons that are in the oxygen chromium bond, all of that is now a good leaving group. But what may not be obvious is that we've had a transfer in ownership of electrons already. I'm going to highlight in blue the electrons that were the lone pair on the oxygen, which oxygen owned. But now those same electrons are in the bond between oxygen and chromium. And I told you that chromium is a good leaving group. And that tells you that if this leaving group left, it would take the blue electrons with it. Okay? That's the oxidation step, right? That's the oxidation step in the sense that the electrons which used to be fully and completely on the oxygen are now in a position where they could leave with the chromium. And I want you to look at this situation where we've got a good leaving group on the oxygen. We're going to sort of call that oxygen the alpha position, and then the adjacent carbon is the beta position. What do we do sometimes in organic molecules when we have a good leaving group on an alpha carbon and then protons on the beta carbon? What have you seen happen there? You can do an E2 reaction where a base removes a proton to create a new double bond and the leaving group leaves. What we're going to do here is exactly the same. A base, hold on for just a minute on what that base is. A base is going to remove one of the beta protons. Electrons will kick down to form a new carbon-oxygen pi bond, and the blue electrons leave with the chromium. So that should give us this aldehyde. I don't like how I drew that, sorry. That should give us this aldehyde. Our leaving group should be this. And it should be a negatively charged chromium, and then we've got the conjugate acid of whatever that base was. If you're counting, the chromium that leaves is chromium 4, not chromium 6. So the aldehyde is oxidized, but the chromium is reduced. As to what the base is that does this proton removal, you'll notice that the chromium leaving group is negatively charged, so perhaps it's that negatively charged chromium from another reaction that does the proton removal. We're not going to worry about that. We'll just allow it to be generic. Okay, so this reaction will convert an alcohol into an aldehyde. And in the same way, it can take a secondary alcohol and convert it into a ketone. I won't draw the mechanism for the secondary alcohol, only the portion where the oxidation step happens. So I'll draw that chromate ester. I still don't like that. There we go. Here's the oxygen from the secondary alcohol. Here's the chromate ester. Here in blue are the electrons that used to be a lone pair on the oxygen. And then here is a base that's going to remove the proton, and the good leaving group is going to leave. And here's that elimination step by removing the beta proton. Electrons kick down to form a new double bond. The leaving group leaves, and that gives you your ketone. You don't need to memorize that a primary alcohol leads to an aldehyde, but a secondary alcohol leads to a ketone. if you understand the mechanism, that is the automatic consequence, right? There's no magic going on here. The reason we get an aldehyde is because of the three things other than oxygen attached to the carbon of a primary alcohol. One proton is going to get removed in the oxidation step. What stays behind is the other proton and the carbon, and that's where we get our aldehyde from. Same thing with the ketone. Of the three things attached to the secondary alcohol, only one is a proton, the other two are carbons. That proton gets removed in the oxidation step, so the other two carbons are left behind, and that's a ketone. Yeah?
So is that ketone oxidized too, like the aldehyde is?
Yes, exactly. So the ketone is the alcohol, secondary alcohol, which has been oxidized, and then the thing that left, the the HCrO3 minus is the reduced form. Yep. All right, good. Yes?
Is the base pyridinium?
Is the base pyridinium? No, pyridinium is already, this pyridinium is already the conjugate acid of pyridine. I'm trying to think, there's no lone pair there to be the base. I suppose one of these double bond or pi electrons could act as the base. I don't actually know. It's a good question. We forgot one thing that's still around. Cl minus was the leaving group after the initial step. I don't really like using Cl minus as a base, but if you have to, it's there. Okay. One important point with this reagent PCC is that I told you it is organic soluble. So this reaction can be run in a solvent like dichloromethane, and there is no water present. That's important for reasons that we're going to see in just a little bit. If there were water present, something can happen to the aldehyde product that may or may not be desirable. There's another set of reaction conditions you're going to see that will take this alcohol, oxidize it to the aldehyde, but will then take the aldehyde and oxidize it to the carboxylic acid. And the key thing that's different is that the reaction conditions that will take you all the way to the acid involve water. So I'll just show you that. We won't have time for the mechanism, but I do want to show you the reagent so that you're ready for it when we come back. You're going to see that oxidation of a primary alcohol to the carboxylic acid follows basically the same steps, but in the presence of water, this can lead to the carboxylic acid. So, as before, we have a chromium-6 reagent, but unlike pyridinium chlorochromate, we're going to use a strong acid, and we're also going to use water. This reaction is called the Jones oxidation. And when I show you the mechanism, you'll see that it's almost identical to what we've done before. The big difference, though, is the water, which promotes formation of the acid. Okay, see you Wednesday.